Earlier, we saw how to derive the algebraic equation for mass conservation for one particular cell for the 2D Cartesian case. Let's think about how that is modified for the axisymmetric case. Let's say that's cell 1 and that's cell 2. So these are the cell centers. And I need to calculate what is the rate of volume flow crossing that face. So we had V dot crossing face between cell 1 and cell 2 is equal to the average velocity at that face, or actually the value at the center of the face. In this case, that's going to be an axial velocity, so I'll denote that as V sub z at the face times the area of the face. Now, in the axisymmetric case, the area you would get by taking that face and revolving it about the axis 360 degrees. Okay, so it's not in the 2D case. If you remember, we took the face and we extruded it by a unit distance, and to get what that what the actual area is. Here you have to revolve it, and so if you looked at that face, you would, and this is not to scale, you would see a cylindrical annulus. And so you can back out, depending on what that distance is and what that distance is, delta r for instance, you can back out what that area is, and that's the area you supply here. So you see, by interpreting this velocity now as axial rather than in the x direction, and changing, so you just need a simple switch in the code to change how you calculate the area when implementing axisymmetric. So once you have the 2D code, you can modify it quite easily for the axisymmetric, but you have to interpret x, for instance, as the axial direction.